We are going to begin to talk about related rates. Wonderful news about related rates is every single one of them is a word problem. And so we're going to be finding some derivatives, aka finding some rates, because derivatives are rates of change. So we're going to be doing some derivatives. And when we do these derivatives, typically we're going to be doing this with respect to time. And we're going to have more than one variable almost always, which means we're going to be doing some implicit differentiation. So all of the rules that we've learned in the past are all going to kind of come into these word problems. But the best thing you can do for yourself is to make sure you draw some sort of a picture, because these directions and all these different things and with our picture are all going to play a role and matter, positives and negatives and all these different things. So let's start to work through first problem. So it says a boat is being pulled into a dock by a rope attached to it and passing through a pulley on the dock, positioned 6 meters higher than the boat. If the rope is being pulled at a rate of 3 meters per second, how fast is the boat approaching the dock when it is 8 meters from the dock? All right, so let's draw ourselves some sort of a picture to it. So I'll do my best on my stick figure kind of drawings here. So we got ourselves a boat, right? And let's say that it's being pulled to the dock, and the dock is here, right? And so actually, let me do this, that we're going to go straight across. And then it says it's 6 meters higher than the boat. So here's the top of the boat, and this is 6 meters. Okay, so, and then we have the rope is being pulled in, and that's where it's being pulled into. All right, so let's throw some values out onto this. We're going to be adding more information than you realize on this. So picture is going to play a huge role. The fact that we have a right triangle, that's going to play a role. All these little things matter. So we're being pulled into the dock. Just make it solid. And the distance is coming in and the rope is being pulled in. So this is shrinking and this distance is shrinking. Those are important. So let's give this triangle, anytime we draw some kind of a triangle, we're going to give it labels, X, Y, and Z. Okay, so like a horizontal, I'm always going to label as an X. My vertical, I'm always going to label as a Y. And then my hypotenuse, I'm always going to label as a Z. Right, so information that we have. We have the Y value specifically is locked at 6 meters, right? And then what we also will be looking at on this information is we're looking at for rates of change. So the change in X with respect to time is maybe a value we know. The change in Y with respect to time is maybe a value we know. And then the change in Z with respect to time is maybe something we know. So let's organize our thoughts. So we are given that our Y value equals 6 meters. Okay. Let's see. We're 6 meters high. So we have that. It says the rope is being pulled at a rate of 3 meters per second. So we are given dz dt. So we're given the rate, and that is going to be equal to 3 meters per second. So equals 3 meters per second. Now, what we're going to add to this is that, yes, that rate is, but it's also a shrinking distance. So our rate is shrinking the distance. So we're going to give it a negative rate, right? And then how fast is the boat approaching the dock? So how fast is the boat approaching the dock? That's this value. We are trying to find our dx dt when specifically how fast when the dock is 8 meters, when the boat is from 8 meters from the dock. So when our x value specifically equals 8. Okay, so that's what we have. So what we got to do is we got to create some sort of an equation that we can do the derivative of, because we need some sort of an equation. And then when we do our derivative, we're going to be creating these dy dt's, dx dt's. So our equation that we have, because we have a right triangle, is x squared plus y squared equals z squared. And then we are going to take the derivative with respect to time. So we got to do all that before we start really plugging in all sorts of information, right? Don't plug it in too early. We're going to do our math first, and then we'll be subbing in what we know and what we don't know, right? So if we do the derivative of this, it's going to be a 2x. Now we are taking the derivative with respect to time, so every single one of these is a chain rule. So this is going to be a 2x dx dt plus a 2y dy dt plus equals a 2z dz dt. All right, so let's kind of look specifically. So this is our generalization, but then we have a very specific triangle that we're looking at, is when this x value is particularly 8. We know the y value is always 6 because it's saying that we are 6 meters. The top of the boat to where the pulley is 6 meters. But they want to know specifically what's happening at 8 meters. Well, when I have these values that I'm trying to plug in, this is the one that I'm looking for, which means I should know all the others. Right, so that's what I'm trying to figure out. So I just use my x value is 8, my y value is 6, my z value is a Pythagorean theorem kind of a thing. So this is actually a multiple of a 3, 4, 5, so a 6, 8, 10. So I have my x value, I have my y value, and I have my z value. Right, so what I need, so I have that, I have that, I have that. What I need to know is what's the rate at which the y value is changing, and do I know what the rate at which the z value is changing? Well, I do know that one. It is shrinking, so we will give it a negative rate. And then my y value, that's not changing at all. That is the height from as the boat's getting pulled in, that thing doesn't change at all. So that's actually 0. So let's plug in what you know. So our x value is 8. Our rate at which the x is changing, we don't know. Plus our y value is 6. Our rate at which it's changing, it's not. And then our z value is 10 at that instant. But its rate is constantly being pulled in at that rate. All right, so let's do our math. So we have 16 dx dt. This is going to go away because of the time 0. And then that's going to equal negative 60. So we'll divide by 16, divide by 16. And so our dx dt equals, if I take 60 divided by negative 60 divided by 16, I get a negative 3.75 meters per second. So that rate is shrinking that distance at this rate at that particular time. And it may not be the same if you were further out or further because the rope is kind of changing and the angle is changing. And this might be moving faster at certain moments versus this moment. So at that moment, this is it. Now that's close to our answer. We got to make sure that we understand what it is that they're asking. And they're asking of how fast is the boat approaching the dock. So that's our answer. However, we are going to be, it's kind of like the difference between speed and velocity. Velocity has a direction to it. Speed is the absolute value of it. So if they're talking about how fast it's approaching, I don't need the negative on there. It's approaching that dock at 3.75 meters per second. So kind of just double check on how it is that they phrase your question of whether you should include direction on it or not. Right? If it depends on how they ask, you might want to include your direction, but you may not want to include your direction. All right, so that was us doing our first related rate type of problem.